Consider the task of modeling a city using an existing shape grammar that can generate a variety of different buildings. The initial result could look very chaotic with random materials, a random height distribution, and mismatching styles within models. We propose a workflow that enables a user to control the distribution of generated buildings. For example, the user might want to subdivide the city into 3 regions, generating small residential buildings for the residential area, office buildings for the financial district, and buildings in the Haussmannian architectural style for the Parisian-like downtown. Procedural modeling is a good way of generating a large variety of buildings to fill our city, but it requires programming skills to create or modify grammars. Even if we use existing grammars, we often want to extract only a subset of the models that the grammar can produce in order to satisfy design objectives. For example, a skyscraper would look strange in the residential area, and a residential building would be out of place amongst the glass buildings in the financial district. Additionally, procedural modeling grammars generate many buildings, including buildings that may not make sense. For example, modern buildings with glass facades do not usually have old red tile roofs, or the quintessential Parisian building with Haussmannian architecture should not be larger than 6 floors. We propose an interactive framework that allows users to obtain their desired set of models. Through user-assigned preference scores, our system learns a probability density function over the shape space of the grammar. We sample the space according to the learned distribution, resulting in a selection of models that fit the user's preferences. These preferences could be for a selection of office buildings, an assortment of natural-looking trees, or a distribution of balanced tables. Consider the goal of creating a shape space consisting mostly of one-legged tables, some tables with crisscrossing legs, and a few tables with 4 legs. All tables should be able to stand on their own. The user is initially presented with a random set of tables from the shape space. The user can interactively tell the system which tables are desired by assigning preference scores to the models. Here we assign a score of 0 to unbalanced tables that would not stand properly, and we assign high scores to properly balanced tables with 1 leg. Since we want a few tables with crisscrossing legs, we assign a low score to this model. For aesthetic reasons, we do not want tables that have bases on each leg, and we assign 0s to those. Using these preferences, our system computes a probability density function over the shape space and resamples the space according to this distribution, resulting in the models on the left. On the right, we show models from the complementary distribution. Again, we can assign preferences to the models according to our goals, assigning high scores to one-legged tables, low scores to tables with crisscrossing legs, even lower scores to 4-legged tables, and 0 scores to unbalanced or ugly tables. Over 5 iterations, our system learns a probability density function that enables us to sample the shape space according to the user's desired models. In the resulting dataset, the orange predicted preference scores indicate a good match to the user's preferences with low uncertainty. There are many one-legged tables, some tables with crisscrossing legs, and a few 4-legged tables. All of the tables are balanced and can stand properly. When providing preference scores, the user can choose different viewing or sorting options. In order to adequately cover the shape space, we can display samples from the complementary distribution, query a list of models that the system is uncertain about, or view a random assortment. Sorting by preference scores orders the models from highest to lowest preference. If the user would like to find models similar to this one, we can sort by affinity using our proposed kernel function to compute the similarity between procedural models. We can extend our framework to work with parametric models as well as grammars. Randomly generated parametric trees can have unnatural shapes. Our system selects a set of trees with natural-looking shapes. We use our system to design a city that, compared to the chaotic city built from random buildings, contains 3 distinct regions with more consistent color, size, and style distributions.